Hello, our viewers. Previously, we have tried to see about vectors. We have defined vectors. We have tried to see the different types of vectors. We have also tried to see about the operations of vectors. We have tried to add and subtract vectors. As well, we have tried to multiply vectors. We have said that the addition and subtraction of two vectors always result in vector. But the multiplication of two vectors results in might be scalar or vector, depending on the type of the product. The dot product of two vectors gives us scalar, whereas the cross product of two vectors gives us vector. It's possible to use the cross product of two vectors using matrix or determinant methods. So previously you have tried to see about that. And today we'll try to see some of the applications of vectors. Applications of vectors, there are different applications of vectors, but mainly here we are trying to focus on the scalar projection, orthogonality of vectors, how to determine the area of parallelogram and the volume of parallelepiped. Therefore, first let's try to see about the scalar projection. And the scalar projection of a given vector, suppose here you have vector b. It's possible to project, or the other ways, to find the component of this vector onto the x-axis and the y-axis. How do we determine the component of this vector onto the x-axis? It's possible to find it to be b cosine of theta. It's also possible to find the component of this vector along the y-axis as b sine theta. Okay? It's possible to project this given vector along the well-known axis x and y. But here we are trying to see how to project a given vector onto another vector. That's what we call a scalar projection. Here you do have vector b and a. It's possible to project this vector onto the vector b. It's also possible to find the projection of b onto a. Okay? Suppose here, let's try to determine, or let's try to project vector b onto a. How do we determine the projection of vector b onto a? Previously, we have given that it's possible to project vector b onto x or y. Whenever you are trying to determine the projection of this vector along the x-axis, you have to drop a perpendicular line to the x-axis. And the distance from this to this is called the projection of this vector along the x-axis, or the component of vector b along the x-axis. This was the usual trend, the well-known trend. But here, it's possible to project vector b onto not a well-known axis, but another vector. How do we project the vector? Therefore, we should have to project or drop a perpendicular line to this vector. Here you have a vector. From the head of this vector, you can perpendicularly project to this vector. This should be 90 degrees. Okay? And the distance from this to this is known to be the projection of vector b along the vector a. Here, the projection of vector b along what? The x-axis. But in this case, we are trying to determine the projection of vector b onto the vector a. It's also possible to find the projection of a onto b. That means if you are trying to drop this perpendicular to the vector B, you can find this to be the projection of vector A onto B. Therefore, how do we determine the projection of vector B onto A? Okay, the distance from this to this, it's possible to use cosine of theta. You might use cosine of theta is the projection of this vector, vector B, onto A, projection of vector A onto B. The distance from this to this is the projection of, B into A. The projection of vector B the projection of vector B, this is the vector B, onto A over the magnitude of this, the magnitude of vector B. Okay? When you crisscross, it's possible to find the projection of vector B onto A as the magnitude of vector B cosine of theta. The same is true, it's possible to find the projection of vector A onto B. That means the distance from this to this is known to be the projection of vector A onto B. This is one good application of vector. It's possible to find the projection, the scalar projection of two vectors. Previously, we know that A dot B can be given as AX BX, AY BZ, BY, AZ BZ. This is how we determine the dot product. And we have said that the projection of vector B onto A can be given as magnitude of B cosine of theta. The projection of A onto B can be given as, if you are asked, the projection of A into B is given to be the magnitude of E, A cosine of theta. Okay? If so, the projection of B onto A is the magnitude of B, as we have previously said that, cosine of theta. And from dot product, we know that A dotted B can be given as magnitude of A, magnitude of B, cosine of theta. This is how we determine. If so, cosine of theta, instead of cosine of theta, you can put it to be A dot B over the magnitude of A, magnitude of B. This is how we put cosine of theta. And you can eliminate magnitude of B by magnitude of B. At last, you can find that the projection of vector B onto A, the projection of vector B onto A is A dot B. How do we determine A dot B? Using this. We have already previously discussed this. Over the magnitude of A. It's possible to find the projection of B onto A as A dot B over the magnitude of A. How do you determine the projection of vector A onto B? If you are asked such question, you should have to put A dotted B over the magnitude of B, the magnitude of B. It's possible to use this way how to determine the projection of one vector onto the other vector. So this is one good application of vectors. The other application, and most important application, is how do we determine the orthogonality of vectors? Orthogonality of two vectors means whether they are perpendicular to one another or not. Two vectors are said to be orthogonal vectors if they are mutually perpendicular to one another. Okay? If two vectors are perpendicular to each other, then they are said to be orthogonal. To identify whether two vectors are perpendicular to each other, we should have to use the dot product. A dot B gives us magnitude of A, magnitude of B, cosine of theta. If two vectors A and B are perpendicular to each other, the angle between them, it would be 90 degrees. If so, when you substitute cosine of 90, you know that cosine of 90 gives you 0. Magnitude of A, magnitude of B, cosine of 90 gives us 0. Whenever you are trying to determine A dot B, if the result of A dot B is always 0, you can possibly say that the two vectors are mutually perpendicular to each other or they are orthogonal vectors. Okay? And A dot B can be determined by multiplying the coefficients AX, BX, AY, BY, AZ, BZ. When you are trying to multiply this, if the resultant gives you 0, then the two vectors are said to be perpendicular to each other or they are orthogonal vectors. Suppose here let's try to find whether those two vectors, those paired of vectors are perpendicular or not. Here you have two vectors. Let's say that these two vectors, let's check whether these two vectors are orthogonal or not. to find whether the two vectors are orthogonal or not, you have to multiply each coefficients. What are the components of vector P? Well, the components of vector P are, we have the I component, okay, 3. We don't have J component or Y component, therefore it is 0. And the component of Z is -1. And here you have Q. The components of Q are -2, 4, and 6. Therefore, you should have to multiply each respective components. 3 by -2 or -2 gives us -6, plus 0 times 4 is 0, plus here you do have -1. -1 times 6 gives us -6. Therefore, -6 plus 0 plus -6 gives us -12. Therefore, these two vectors are not orthogonal, because whenever you find the dot product of two vectors, it should give us 0. If it is 0, you can say that they are orthogonals. But here it gives us -12. Now let's try to check whether these two vectors are orthogonal or not. What are the components of the vector n? Vector n. We don't have I, therefore it is 0. We don't have j, 0. The only thing that we have is the k component, it is -9. And here, vector O, we have vector O. The component of vector O are -2 or -2 is I component. The j component is 4, and we don't have the z component. Now let's try to multiply j with j, k with k. So 0 times 2 gives us 0. 0 times 4 gives us 0. We should have to add these two. And at last, when you multiply 0 by 9, also gives us 0. So when you add these zeros, it gives us 0. Therefore, you can say that vector n and vector O are perpendicular to each other. They are orthogonal vectors. You can proceed on this too as well. You can check whether they are orthogonal or not. So the other applications of vector is to check whether two vectors are perpendicular to each other or not. Previously, we have said that the scalar projection, and the other way is to find the orthogonality of vector. And the other point is collinearity, or we can say that it's possible to check whether two vectors are parallel or not. How do you determine whether two given vectors are parallel or not? Is that we should have to use the cross product. Okay, the cross product of the two vectors gives us 0. It means that they are orthogonal, collinear vectors. Let's take here. Suppose you do have two vectors here, x in the I, ay in the j, az in the k, and b is also given like this. If these two vectors are collinear, or if they are parallel to each other, then one vector is the scalar production of the other vector. It's possible to say that vector A is alpha times B, where alpha should be a number, a pure number. It might be 1/2, or it might be twice of that of vector B, and so on. If it is possible, that it's possible to say that the two vectors are parallel. And the other technique is, you should have to check the ratio of each components. Here you have the two vectors. It's possible to use ax over bx, the ratio of x, bx. If it is equals to ay, by, if it is equals to az, bz, then it's possible to say that the two vectors are parallel vectors. So it's possible to check whether these two vectors are parallel or not. Here you have two vectors. Let's say that p and q. 3 in the I minus k. To check whether these two vectors are parallel or not, you can find that the I component with I, there is no j component, okay? The k component with k. Therefore, 3 divided by minus 18, okay? You have to check whether these are equal or not. -1 over 6. -1 over 6. Therefore, when you try to simplify this, it gives you -1 over 6 is equals to -1 over 6. They are equal. If this is equal, it's possible to say that these two vectors are the parallel vectors. Or it's possible to say that vector P can be given as, here let's take that, vector Q is minus 18 in the I plus 6 in the K. Can be given as 6 times vector P. Vector P. So when you are trying to multiply vector P by 6, okay, if you are trying to multiply this by 6, 6 times 3 gives us, negative 6. If you are trying to multiply by negative 6 times 3 gives us negative 18. Negative 6 times negative 1 gives us positive 6. It's possible to say that alpha times B can be given us whether the two vectors are parallel or not. And now let's proceed. The other good applications of vector is it's possible to determine whether two vectors, it's possible to determine the cross product of the two vectors. If you are trying to determine the cross product of two vectors, it's possible to find the area of a parallelogram. Suppose here you have a parallelogram. Well, parallelogram is a quadrilateral, a four-sided figure whose opposite sides are parallel, okay? And to find the area of this vector, we know that area of rectangle, triangle, and so on can be determined using the product of its lengths and its breadths, okay? Here you have the breadths or the lengths to be the magnitude of B. You have one of the side is given using vector B. The magnitude of vector B, times the height, okay? This is the height. You have to perpendicularly drop this. This is called height. And the height can be determined using trigonometric rules, that you know that sine theta is opposite over hypotenuse. Opposite is the height itself, h, and the hypotenuse is there is a vector. It is given in vector. You have to find the magnitude of that vector over the magnitude of vector A. And when you try to crisscross, the height gives you the magnitude of vector A sine theta. And we know that area of a given parallelogram or a given rectangle can be given as area. This is area is length times width. The length is, in this case, B, the magnitude of B. The height, h. And h can be represented using magnitude of B times the height can be given as magnitude of A sine theta. And this is the area. And the magnitude of A times the magnitude of B sine theta means you are trying to determine the magnitude of the cross product of the two vectors, A and B. Magnitude of A cross B, when you are trying to determine this, it's possible to find the area of the parallelogram. This is what it says. Here, the magnitude of A can be determined ax squared, ay squared, az squared. The magnitude of B as well, you can determine using this technique. And the area of the parallelogram can be given as the magnitude of B times the height. But the height, we have said that magnitude of A sine theta. A sine theta means you are trying to determine the cross product of the two vectors. The cross product of the two vectors, and then when you are trying to determine the magnitude, you are trying to find the area of a parallelogram. Suppose that, let's say that you have a parallelogram whose sides are given to be 2 in the I plus 3 in the j, let's say that. And you have one of the other side is to be minus I plus 2 in the j plus 4k. Okay? If it is given like this, what is the cross product of the two vectors? That is how we determine the area of a parallelogram. The sides of the parallelogram is given to be, one of the side is in this 2 in the I plus in the j, and the other side is given to be minus I plus 2j plus 4k. Therefore, the area of a parallelogram is always try to determine the magnitude of the cross product of the two vectors. And how do we determine the cross product? Well, you have to put it in the I, j, k in matrix form. Therefore, the component of I is 2, the component of j is 3, and the component of k is 0. Here you have minus 1, here you have 2 and 4. Therefore, you have to find this cross product. I, you have to eliminate I, row and column. 3 times 4 gives you 12, minus 2 times 0 is 0, plus, and you have to eliminate all the row and column. If you use plus in the J, first you have to take K. 0 times minus 1 is 0, minus 4 times 2 gives you 8, plus K. If you eliminate the row and column, 2 times 2 gives you 4, minus 3 times minus 1 gives us minus 3, negative 3. Therefore, this gives you 12 in the I, 12 in the I, and this gives us minus 8 in the J, and this minus could make it to be plus 7 in the K, okay, 7K. This is a vector, this is the vector, this is not the area actually. We are trying to determine the area of a parallelogram, If you are trying to determine the area of a parallelogram, you have to find the magnitude of this vector. That's what it says, the magnitude. And how do you determine the magnitude? Well, the magnitude can be determined as 12, the whole squared, plus negative 8, the whole squared, plus 7, the whole squared. This is how we determine the area of a parallelogram, So one of the applications of vector is to find the scalar projection, the other is orthogonality of the vector, and the other is the area of a parallelogram. And at last, it's possible to find the volume of a parallelopiped. The volume of parallelopiped can be determined using a vector product. And parallelopiped is actually a force whose base side is parallelogram. It's a figure whose base is parallelogram. Here you have a base, and its base is parallelogram. Therefore, volume is base area times height, and it's possible to use a mathematical approach of that. One of the side is given to be A. The other side of the parallelopipe can be given B, dotted with C. Therefore, you should have to find A cross B. Whenever you are trying to determine A cross B, it means that you are trying to determine the area of a parallelogram. Previously, we have said that the cross product of the two sides gives us area. And the area multiplied by, dotted by, C gives you the volume. And this is known to be triple scalar product. So A cross B dotted C, or C cross A dotted B, or B cross C dotted A can give us the volume of this parallelopiped. So far we have tried to see the applications of vector. Vectors can be highly applicable in mathematics and in physics. Mainly in physics, we have seen how to find the scalar projection of a given vector. It's also possible to find the orthogonality of two vectors, meaning whether the two vectors are parallel or not. It's also possible to find, using vector, whether the two vectors, given two vectors are parallel or not, or collinear vectors. And we have also seen that the area of a parallelogram can be determined using cross product. And the volume of parallelopiped can be determined using a triple scalar product. So this is all that I've got for today. Next time we'll try to see about some basic concept about kinematics. So see you then.